alcohols. So we ended up with modifications. So we were looking at substitutions. And we have the SN1 and the SN2 substitutions, SN2 being often more productive in synthesis, but in some cases, SN1 is the only way to do that. And we looked at specific modifications, HCl and zinc, right, for a primary. This is an SN2 type process, right? We ended up there with that one. We looked at the thionyl chloride with pyridine. And then we ended up with the bromide form of that, which is actually the phosphorus tribromide. And so let's look at the mechanism for that one. It's similar because what we're going to do first is make a good leaving group. So the first step of these is to make this a better leaving group. So we have our alcohol reacts with our phosphorus. Okay, so oxygen does a nucleophilic attack on the phosphorus. We lose one of our bromines. We have the positive. Now we've got a decent leaving group. The bromide that just left is going to be our nucleophile. So the bromide comes in an SN2 style process, kicks off this. Electrons go towards the leaving group. And then this gives us our bromide plus the phosphorus compound. Okay, the reaction of the oxygen to the phosphorus is really driven from oxygen phosphorus making really strong bonds. Phosphates are the most common form of finding phosphorus. Phosphorus is white phosphorus is not have the oxygen, but if you put that on an end of a match with a little wax over it, as soon as you scrape off the wax, which is what you're doing with the match, when it comes in contact with water and oxygen, it actually catches on fire, right? So exothermic that it catches on fire. So the oxygen phosphorus interaction is very strong. That makes strong bonds. And so that's what the driving force is here. But then once we form, that's what the driving force is here. But then once we form this, right, then it's just a good leaving group and a nucleophile coming in and kicking off the leaving group to end up giving us our product. Okay. All right, so those are our substitutions. So these are, I'll note these, right? This is new, right? But then the SN1 and SN2 are review reactions. Okay, if we can do substitutions with alcohols, then we should be able to do eliminations with alcohols. So that's our next section. And if we use concentrated H2SO4, we can get an E1 type elimination, right, to give us the CHEM3053 product. And of course, in E1, the CHEM3053 is going to be favored. So that's going to be your major product. We could also take the alcohol, use our tosyl chloride to create a good leaving group, and then use a selective, in this case, I'm going to use a big bulky base, and that big bulky base will give me the Hoffman product. So what happens here, right, is we first create our good leaving group, right, and then we do an elimination. Any questions about either of these? In the first one, it's important to note that the big difference here is we have a concentrated sulfuric acid, but we're also using a non-nucleophilic acid. So sulfuric acid or phosphoric acid. If we had used, you know, HCl, the Cl is nucleophilic. And then if we had done an S-1 reaction, right, with a good nucleophile, HBr, HCl, the chloride and the bromide are nucleophilic, where when you use the sulfate, it's non-nucleophilic. So if you ever hear me talk about non-nucleophilic acids, what I'm talking about is the conjugate base is not something that would attack a good electrophile. So it's usually things that are very stable, like sulfates and phosphates. Right, and of course here, we just are going to create, activate that, and then that allows us, in the case of bulky, we would get the Hoffman product. If we'd used a small base, then we would have gotten the Saitsev product. Okay. The next area we need to look at, right, and that's review, and I'll spend a lot of time on that. We'll do some try this later today, and then on Wednesday, we'll do review on Wednesday, and we'll see some more practice with that. The next is oxidation of alcohols. So if we look at our types of alcohols, if we start with a tertiary alcohol here, and we try to oxidize this, right, we're going to get no reaction. Right? Because if we look at it, we have no protons to be to leave. But if we look at a secondary alcohol, and let me color code this, right? So there's a hydrogen, right? This one had no alpha hydrogens, right? But here we have at least one alpha hydrogen. So if we add an oxidant here, we could end up with the carbonyl, or we will end up with the carbonyl with the right oxidant, right? And what we're losing, if we think about it, is these two hydrogens. So a secondary alcohol will become a ketone, right? And a tertiary alcohol, right, no reaction. If we have a primary alcohol, now we have two alpha hydrogens. We could remove one of those alpha hydrogens to get us to the aldehyde. But because that's a hydrogen there, I could also oxidize this one more step to the carboxylic acid. So primary alcohols can go to aldehydes, and depending on the reagent, I can go to carboxylic acids. In the case of the secondary alcohol, I would have to break a carbon-carbon bond. There is a process to do this, but it's kind of a radical insertion process, not a simple oxidation. And you won't see that until organic too. Right now, if we think about simple, straightforward oxidations, we're not going to be breaking carbon-carbon bonds. So therefore, secondary alcohol ends up with ketone. Primary alcohols could stop at the aldehyde or could go all the way to the carboxylic acid. Our main oxidant is going to be chromic acid. And chromic acid is this species. Now, this is very unstable, right? It's a good oxidant. It's a very strong oxidant, but it's also very stable. So what we do is we make this in situ. So we don't put sulfuric, we don't put chromic acid in solution because it's not going to exist for very long, and it has a tendency to oxidize, all kind of stuff. So we create it in situ, right? So in solution, we're creating this by either adding chromium anhydride, that's what this is called, CrO3, and acid, or we could add sodium dichromate, a little bit easier to work with, but a little bit more expensive, right? Usually they show this one with sulfuric acid and water, but they can also show it with just H3O+. So you'll see both of those. So whenever we talk about chromic acid, we're not adding chromic acid. This is going to be confusing, but we can either add the disodium dichromate, or we can add the chromium anhydride. Right, and you can see the chromium anhydride, it looks like the chromic acid except it's missing water. And then over here, this is sodium. It's sometimes called disodium dichromate. Or sodium dichromate is more accurate than disodium dichromate. Disodium dichromate is an older term. Okay. So these are our reagents. So what happens? Well, if we add a secondary alcohol with one of these sets of reagents, we will end up with a ketone. Or we could have done the sodium dichromate. The oxygen reacts with the chromium, and then we get a deprotonation of that alpha hydrogen to create the carbonyl. The book has the mechanism. I'm not going to expect you to recreate that mechanism, so I'm not going to take the time to draw it right now. But if you want to look at it, you can look at it. It explains the fact that the water is essential in this process. If we have a primary alcohol, and let me erase that and redraw that. I have a primary alcohol and I use one of the chromic acid salt reagents. I'm not going to end up with the aldehyde. I'm going to end up with the carboxylic acid. Now the process does go through the carboxylic acid. Does go through the aldehyde. But it's not easy to isolate the aldehyde. It has been done to prove that the aldehyde is the intermediate between these two steps, but it's not something synthetically that can really be done. Now, how to stop here? We could stop here if we could limit So if we could limit the amount of water in the reaction, we could potentially stop here. And that's actually one of the ways they tried to isolate this to prove the mechanism. But notice that both of our reagents, right? The solvent is actually water. So what we need is something that behaves like the chromic acid, but that we can put in a non-aqueous solvent. So we can limit that and potentially stop at the aldehyde. So the reagent that we use for that is PCC. PCC is pyridinium. Chlorochromate. All right, so we got a chloro, this, so pyridinium. All right, so PCC. This, because of the pyridinium, is organic soluble. Because it's organic soluble, then I can put this in. I can put this in an organic solvent, especially an anhydrous one. And our favorite anhydrous is the methylene chloride. And we can stop at the aldehyde. So the pyridinium chlorochromate, because we're limiting the water, allows us to do a one-step mechanism here. It turns out also the pyridinium chlorochromate, even if we added water, does not easily go to the carboxylic acid. But so now we've got a way to stop at the aldehyde. It also works with secondary alcohols. Right, to form ketones. So if we look at primary alcohols, if we use one of the chromium acids, right, we'll end up with the carboxylic acid. If we use PCC, we'll end up with the aldehyde. If we use a secondary alcohol, whether we use the chromium anhydride in acid, we use a sodium dichromate and acid, or the PCC methylene chloride, all right, we're going to end up with the ketone. Okay, questions about these? Does anybody see the problem with these oxidants? Especially if we were trying to make pharmaceuticals. Well, all of these oxidants use what? Chromium, right? Whether it's chromium anhydride, sodium dichromate, or PCC chromium, right? It's a heavy metal, so we want to limit that. So therefore, the chromium, right, is not horrible in small amounts, but it's not something you're going to want in large amounts. So you do want to control your chromium, right? So therefore, if we were looking at pharmaceuticals, we want a different way to do this that doesn't use a toxic metal, right? Just like with our osmium, we wanted to decrease that. So there are a couple of oxidations the book focuses on. There's actually whole books made on alcohol oxidations, but two that have become very popular are Swarn oxidation, and a new one that's come around in the last 15 or so years as being popular, the Dis-Martin. Okay. So Swarn oxidation uses DMSO, DMSO, and this acid chloride compound followed by triethylamine to give us the carbonyl. The first step of this is actually to the DMSO and the, I can't remember the name of that compound, together react to give us our starting material. So DMSO, we've seen this one before, right? Sometimes you'll see it drawn as this, right? So for the mechanism, we're just gonna show it as a zwitterion where we have the positive and the negative. Then we've got our carbonyl chloride here, our carbonyl chloride here. And let me clean this up. So at this point, we get nucleophilic attack at one of the carbonyls. And then the oxygen comes back down, kicks off the chlorine. And then we get a nucleophilic attack of the chlorine onto the sulfur. We get these electrons coming back around to create a double bond there. We get the electrons here going towards the oxygen, kicking off the chloride, right? So we get a cascade. We've seen this in a couple of other mechanisms. And the nice thing about this is what we end up with is this dimethyl chloride species, plus we get CO2, right, which is a gas, CO, which is a gas, right, plus the chloride negative, which becomes the counter ion of, so when you're done with this, right, you don't have any other reagents you have to worry about. You've made the reagent and everything else is a gas. So then the next step, so that's preparing your reagent. The next step is reaction with the alcohol. So the alcohol reacts with the sulfur. We get a leaving group leaving, so nucleophilic attack, leaving group leaves. Still have the positive on the oxygen, on the sulfur. But then now triethylamine, and I've kind of shown it in a bad place, but that's okay. We'll just draw a really long arrow. So this comes all the way over here, deprotonation. So we get a transfer, so we get nucleophilic effect, followed by a proton transfer, right? Base picks up proton. Let's turn the corner. I'm gonna put an extra couple of electrons in here. Then our nitrogen picks up a proton from this methyl. Okay, and it took them a while to figure this mechanism out because it's not what you would have thought would happen. Then this electron picks up this. Oops, that needs to be a 2. Right. then that will kick these electrons here, which kicks these electrons back to the sulfur. And I should have put a positive on the sulfur. Giving us the carbonyl plus now methyl sulfide, which is also a gas. So the nice thing about a Swarren oxidation is this whole process can occur, and what you're left with is just the product, some gases given off. It smells bad because dimethyl sulfide is what they put into natural gas as a odorant meaning to make it smell, and then the salt, the triethyl ammonium chloride salt, right? So that's the Swarren oxidation mechanism, right? So way it would look, it works also with the primary, right? So if we use a primary, it will just do the one reaction. So DMSO, don't know why I keep drawing that. Oh, remember to put the parentheses and then the 2. Right, then the triethylamine. Big, long, complicated mechanism, but the important part of this is you end up with gases and a salt, and in the second step, you end up with a gas, and we'll go ahead and draw it out, a salt, right? So nice, clean, easy to work up. Don't have to worry about mercury, don't have to worry about chromium, and don't have to worry about chromium cleanup, right? Here we end up with just some gases and a salt. Okay. So it works with primaries, works with secondaries, nice, clean, probably one of the more favored reactions you'll see most real organic synthesis people doing is going to be this one. A similar one, the issue with this one is that this species here, okay, this species here, because it's an acid chloride, isn't very stable to certain functional groups, right? So this works perfectly fine with all I have is an alcohol, but this could also react with amines and other reactions. So we want to make sure that we have an alternative. That's the Dis-Martin or Des-Martin, which always makes me think of, I don't know why Desi Arnaz, but Des-Martin. Use DMP, and I'll show you that in just a second, again, without water to get the aldehyde. And the DMP is this compound. Kind of unique from the standpoint that it has an hypervalent iodine. And then the OAC is acetates. So that's the DMP. Not going to worry about showing the mechanism. It is in the book. It's not quite as slick as the Swarren oxidation, but it works rather well. But we can do this with both secondary and primary. To get the products. Questions about these? Okay, so that was the end of 1210, right? So that's what we're going to be doing. So therefore the exam is going to be chapter 9, 10, 11, and 12 through 12, 10. Okay, let's do some try this. Start with some simple things, and then we'll do some synthesis. I'll put down let's do some select the reagents first. Okay, let's take a little time to come up with some reagents for this one. Okay, question in the chat. What you should use as your guidance is the learning outcomes. And so most often, if the learning outcomes weren't highlighted, if a subsection or a chapter, a section of a chapter wasn't highlighted in the learning outcomes, I didn't cover it in the lecture. But it's worthwhile reviewing the learning outcomes to see if there's going to be something focusing on that. So the learning outcomes are there to guide you in that. In most cases, I covered all the sections that would have been on the learning outcomes. But just because I didn't cover a section, if it's in the learning outcomes, you should review that. A couple of reasons. One, I use the learning outcomes when I'm picking questions for the exam, but also most of the organic faculty know those learning outcomes and use those learning outcomes as the basis for their organic 2. And so, you know, when you get to organic 2, there will be expectations of you knowing those learning outcomes. So I don't ask every single question from every single learning outcome, but I can ask a question from every learning outcome. Okay, those learning outcomes are something that we developed about 8 years ago, and most of the faculty still refer to those. So it's probably about time for us to do it again. If we look at here, we have oh, that was probably really hard. I meant to put an H there. So let's say we put an H there, then this becomes pretty straightforward. We could use PCC and methylene chloride, right? Or we could have used the sworn oxidation, and I'll just put sworn here, or we could have used the Des Martin. Okay, so going from a primary alcohol, all 3 of these would have worked. If we look at the next one here, we could have used the E2 type reaction, H2SO4 concentrated, or we could have done the tosyl chloride, pyridine, followed by a base, and here any decent base would work. The last one, again, we could have used the H2SO4. I guess I didn't make these very challenging. Concentrated, right? Or we could have done the tosyl chloride and pyridine, but in this case, we do need to specifically make sure that we use a smaller base. You don't want a sterically hindered base here, or you end up with the Hoffman elimination products. Okay. All right, now let's do some where I give you the reagents and you give me the products. we have a question? Let's take a little bit of time. This first one, okay, this is going to be a sworn oxidation conditions. So we're going to end up oxidizing the alcohol to a ketone. The second one, we're doing a E2 type elimination. We're using a bulky base, right? Tert-butyl potassium terpentoxide, right? And so that's going to give me the Hoffman base, a Hoffman product. And then the third one, we're using the PBr3 on this one. The trick is to remember that this is going to be SN2. So therefore my bromide adds down. Any questions about either of these three? Okay, let's try a few more. If you needed to get the answer for the last one, just scrolled up. Okay, so let's take a look at these three. So if we look at the first one, right, we're reducing a ketone to a alcohol. That wasn't today, we saw that earlier, right? So we could use sodium borohydride in methanol, right? Or we could have used one lithium aluminum hydride followed by water, right? The next one, we're going from an primary alcohol to a carboxylic acid. None of the carbon skeleton is changing, right? So here we could have used the chromium anhydride, or we could have used the sodium dichromate and acid and water. And the next one, we're going from a secondary alcohol to a ketone, right? But there's also an alkene, and the alkene is going from the alkene to the alkene, right? Nothing is happening to the alkene. So going from a secondary alcohol to a ketone, any of our oxidants would work for this. But because of that alkene, there's going to be some that are going to be better. What's the problem with the alkene and let's say the chromium acid oxidations? Will an alkene react with acid and water? Yes. So if I use the chromium acid conditions, either chromium anhydride and acid or sodium dichromate and acid, right, the alkene could react with the acid and water. So therefore, the preferred reactions here would be something without acid and water, right? So PCC and methylene chloride would work. Or I could use the Swarn oxidation conditions, right? That one wouldn't react with the alkene. Or I could use the Des-Martin conditions. So the only two reagent conditions I would want to use is the sodium dichromate here. Okay. All right, let's try some retrosynthesis. And we'll give you more time on these. So. And sorry, these aren't going to be retrosynthesis. I drew it backwards. So let's do retrosynthesis. Okay. And let's take, so I don't go too fast, I'm going to put a minute in here. Remember, with retrosynthesis, we need to watch our carbon skeleton, and then we need to think about our functional group transformations. You can go from the starting material to the target molecule, or you can go backwards from the target molecule to the starting material. And sometimes to figure out, you need to go both forward and backwards. Okay, so let's take a look at the first one. And let me get this one out of the way. So if we start with the starting material, right, we have 1, 2, 3, 4, 5 carbons over here. Over here, we have 1, 2, 3, 4, 5 carbons. If we think about our functional group, we have the alkene on the 1, 2. We have the carboxylic acid on the 1. So therefore, we don't have to worry about carbon skeleton change to carbon skeleton. So then we need to think about how can we get to an alkene, right, to a acid. Well, how can we make an acid? Right now, it's pretty straightforward. We only have the alcohol to make an acid, right? Or we could have cleaved a double bond, but cleaving a double bond and then ozonolysis, right, would have been would have lost carbons, right? So without a carbon change, we go from a primary alcohol to a carboxylic acid. And can we get from an alkene to a primary alcohol? Well, yes, right? So therefore, our mechanism, our process here is we're going to form right the anti-Markovnikov addition of an alcohol to give me the primary alcohol, and then I'm going to use, you know, like sodium dichromate to oxidize that to the carboxylic acid. And I could have used, if you used the chromic anhydride conditions, those are the same. But we have to regioselectively add the alcohol and then oxidize that fully up. Sworn wouldn't work with here, PCC wouldn't work because they'd all stop at the aldehyde. On the second one, right, and we're getting low on time, so I'll go ahead and answer this. We're starting with 3 carbons. But over here, we have 5 carbons. So we know we're going to have some type of change. Now, if we think about where our groups are, if we said this is 1, 2, and 3, this oxygen could be, we could be looking at these 3 carbons, right, at the same position, which means we're adding those carbons. Right, so if we think about where that could add, now if we think about adding carbons to an alcohol, we don't have a way to do that, but we do have a way. If we oxidize this to an aldehyde, right, I could add 2 carbons using the Grignard, right? So the Grignard is a great way to add carbons. That would end up giving me this, right? That would be the product of that. And then could I take this to that? Right, so I could oxidize the alcohol to the ketone. Can I take the primary alcohol and get an aldehyde? Yes, right? So the trick in this one is to think about the ways that you can add your carbon and realize that the acetyl acetate, right, doesn't work well, but the Grignard works very well, right? So the reaction for this one, we're going to take and oxidize, and there's several different reagents, right? We could use this or the Swarn or the Des Martin, right? That gives me my aldehyde. Then I'm going to react that with my Grignard. Right, followed by water to reprotonate. Oops. Let me turn that corner. That then gets me to my base structure here. And then I can oxidize here with either PCC or the chromium. Since there's no other functional groups, any of the oxidants could actually work well here. Okay, and that's